Hey everyone, welcome to day 4 of our derivatives and integrals challenge. So today for our derivative, we're going to use the quotient rule, the chain rule, product rule, a bunch of stuff. And for this integral, we're going to use a u substitution, which hopefully will kind of give a cool result. So for the derivative, we're going to start off by applying the quotient rule. So that means we want the derivative of the numerator times the denominator itself. And so for the derivative, we're going to write f prime of x is, okay, the derivative of what's on top, that's going to be a product rule. So that'll be 2x times the cotan of x plus x squared times, I forget what the derivative of cotan x is. Let's do that over here. ddx of cotan x, as you know, is the reciprocal of tan, which means is really just cos x over sine x. And so we can apply the quotient rule. And so that'll be the derivative of the numerator times the denominator. So that'll be negative sine x times sine x minus the numerator times the derivative of the denominator. So minus cos of x times the derivative of sine x is cos x. And that's all over sine x squared, or sine squared x. And that'll be, that's negative sine squared x minus cos squared x all over sine squared x. And that means that's negative sine squared plus cos squared. So that's negative 1 over sine squared. And that's negative cosecant squared x. Nice little real-time derivative here. So that'll be the derivative of this part of the product rule. So x squared times negative cosecant. I'll pop that in there, and I'll make it negative x squared cosecant squared x. And that's times the denominator. So that's times ln of x squared. Oh boy, okay. Minus x squared cotan x times the derivative of the denominator. So that'll be times, that's 1 over x squared times the derivative of x squared itself. And that is 2x. And pretend that this is all of our numerator. And so we'll have that over the denominator squared, which will mean the ln squared of x squared. Or if you'd rather, that might be a little bit confusing to read, that'll be the ln of x squared, let's say. Let's see if we can clean this one up. I'm guessing we can. Okay, in the first part, I don't know if we can. What is there in every term? Okay, so at the very least, in this last term, the x squares cancel out. So all we have is 2x cotan x. Okay, and we have a 2x cotan x there too. That's kind of cool. So I guess we can kind of factor that out. We could do, I'll use the green marker here. We could do 2x cotan x, 2x cotan x times, I don't know if this is really simpler, but whatever, we'll try it, times ln of x squared minus 1, right? And then we still need this part, so minus x squared cosecant squared x ln of x squared all over the ln of x squared squared, which really we could write ln of x squared as, we could write that as using logarithm laws as 2 ln x, and then we could square that whole thing, and we could write that maybe a bit simpler as 4 ln. No, that's probably as easy as we'll get it. That'll be 2 ln x squared. And I'd say that's as simple as it'll get. So let's leave it at that. That'll suffice for today. Treat this as just an intermediate piece of work. Hopefully you found that useful. This is one of those things for cotangent x. You might want to just commit this to memory. The derivative of cotangent x being negative cosecant squared. But remember, if you ever forget, same thing for tan or any of the reciprocal trig ratios, remember you can always just rederive those derivatives by applying the quotient rule, and it won't take too long, right? Okay, so for this one, on that note, kind of a nice segue, we're going to evaluate the integral of tan x dx, which is really the integral of sine x over cos x dx. And when we write it that way, this might pop out at you as suitable for a u substitution. So let's go ahead and try one. I'm going to suggest let u be, well, let's think this through. If we make u the numerator, if u is sine x, then the derivative is cos x dx, but that's not going to appear in the way that we want it to because the cos x is in the denominator, the dx is in the numerator, right? And so that's not going to work well at all. What'll work much better is if we make the denominator, the cos of x, be our new variable u, then our du is going to be exactly what we need it to. It's going to be, I mean, there'll be a negative in there, but it'll be negative sine x dx, right? And it's the sine x dx that we have to grab. And so if we push in the negative, divide both sides by -1, let's say, and so we get negative du is equal to sine x dx, and so we can substitute that in, and so our integral becomes, let's say the negative can go outside, right, as a constant of -1, so the negative integral of du will replace sine x dx in its entirety, so we'll have du over cos x, is that u? Or if you'd rather, I don't know, maybe if you're not used to seeing it written like this, maybe I'll just leave it as 1 over u du. That's a d. My goodness. There we go. Thank you for your patience. And now this is likely an integral that you're at least somewhat familiar with. That's going to be the ln of u. And so evaluating that indefinite integral, we're going to have the negative ln of the absolute value of u plus c. And let's resubstitute back in our original variable x. And so we'll have the negative ln of the absolute value of cos of x plus our integrating constant c. And we're done. So I hope you found that useful. I really do encourage you guys to try these on your own before you watch me go through them and then compare your answers. I hope you found this useful. There's different ways of simplifying this. Don't worry if you didn't simplify it exactly the same way that I did. I'm sure there are other ways that would be kind of just as good. So I hope you enjoyed this. If you guys have any good questions for future videos, please leave a comment down below. And thanks for watching.